Good morning, students. We're going to be going over Unit 6, Lesson 5, using the a-value of a quadratic function. Your learning objectives for today are to identify the a-value in a quadratic function, then use that a-value to find the pattern of change. We have talked a little bit about this year, where we've discussed how the a-value, the scale factor, the vertical stretch or shrink factor of a quadratic, if we multiply that by 1, 3, and 5, that will tell us what the pattern of change is. Additionally, we're going to use that pattern of change to write an equation of a quadratic function in all three forms. So take a second, pause the video, do this warm-up question, and then we will go through answers. When I look at all three of these forms, the one thing they have in common is they all have an a-value. This a-value is consistent throughout each form, so the a-value is what each has in common. What does this a-value tell us about the graph? Well, it kind of tells us if our graph is vertically stretching or shrinking. It tells us if our graph has a maximum value or a minimum value. And then it can also help us find the pattern of change, which, if you remember from yesterday, the pattern of change is always a times 1, a times 3, and a times 5. And this pattern tells us the vertical distance between perfect points on a quadratic function. Looking at these two graphs, the thing I notice about the 3 points given on the first graph is that my 3 points have a distance of 1, then 3, then 5. There are no perfect points between these 3 points. Therefore, I know that my a-value is 1. The number I would multiply by 1, 3, and 5 to get to 1, 3, and 5 is 1. Compare that with this next graph, where your pattern or your values between those perfect points is 2, 6, and 10. So 2, 6, and 10, what that tells me is that I multiplied 1, 3, and 5 by something. Now, what did I multiply it by? I multiplied them by 2. They all doubled. So that tells me my a-value is 2 for the second graph. The other thing the a-value tells me, it doesn't just tell me the shape of the graph and whether my graph will be vertically stretched or shrunk based off of those vertical distance of perfect points, but it also tells me if my vertex is a minimum or a maximum value. If that a-value is greater than 0, I know for certain a minimum value will exist on my function. If a is less than 0, so a is negative, I know that the vertex is a maximum value. Kind of look at these two graphs to confirm that in your head. On this first graph, I know that my a is positive because I have a minimum value. I know that a is negative on the second graph because I have a maximum value. For these two examples, we're going to determine the a-value given the graph. So the thing I need to do is I need to first find perfect points, starting with my vertex. So my vertex, being a maximum value, what that tells me is my a-value is for sure negative. Now the next thing I notice is that there's like a perfect point that is 3 units away from that vertex. The next thing I notice is that there is another set of perfect points that are 9 units away from that vertex. So what this tells me is that I scaled. My a-value got larger. So this tells me my a-value is not 1. My a-value, how did I go from 1, 3, 5 to 3, 9? And I know we don't have a last coordinate here because it's way off the graph, but what I'm able to say with certainty is that my a-value is not only negative, but it's also a multiplication of 3. So for this first graph, my a is negative 3. Make sure to do a negative 3, not a positive 3. For this next one, I notice that I have a minimum value. So because I have a minimum value, I know my a is positive. And I also notice that I have perfect points that are 2, and 6, And I can't find this last one because it's off the graph, but I can kind of assume it's going to be, you know, some multiplicative that I got to 2 and 6 by. So once again, that pattern of change, 1, 3, 5, went to 2, 6, and I don't know that last one, which is okay. Like, how did I get from 1 to 2? Well, I multiplied it by 2. So that means that my A value is 2. For this next one, we are going to identify the A value using the pattern of change. We're going to write an equation of the quadratic in vertex form, and then we're going to use vertex form to write the equation in standard form. So some of this is a little bit of review, but I want to start with that A value. So what I see is that I have a perfect point for my vertex, which is a maximum value. So because it's a maximum value, I know that A is negative, okay? The next thing I notice is that I have a set of perfect points that are 2 and 6 units away, so I kind of can assume that my A value is 2. Sorry, it's a negative 2, okay? So that means that my pattern of change, it wouldn't be 1, 3, 5, it would be negative 2, negative 6, negative 10, because I'm multiplying those 1, 3, and 5s by those negative values. Next up, write the equation of the quadratic in vertex form. So just a reminder, the vertex form equation, which you will be given on your exam, is y is equal to a times x minus h squared plus k. So the things that are given to us, or that we're going to find, are a, h, and k. So luckily, I just found out what a was. It's negative 2. So the only things I need to find are h and k, which are my vertex. So in this case, my vertex is negative 5, comma 4. So negative 5 is going to be substituted in for h, and then 4 is going to be substituted in for k. Just don't forget to simplify, because if you have a negative 4, really what that should turn into is a positive 4, and that is your vertex form equation for this quadratic. Next, we're going to use vertex form to write the equation in standard form. So we did this on Tuesday this week, where we first expanded that x plus 4 squared into x plus 4 times x plus 4. Then we FOILed, so we're going to do x times x, which is x squared, x times 4x, which is 4x, 4 times x, which is 4x. Those combine to give you 8x. And then finally 4 times 4, which is 16. Don't forget to bring down that positive 4. Then after I FOIL, I'm going to distribute that negative 2. So this would become y is equal to negative 2x squared, negative 16x squared, minus 32. Don't forget that positive 4. Then finally, the last thing I need to do, I just need to combine like terms at the end there. So my standard form equation should be y is equal to negative 2x squared minus 16x minus 28. So what I've done is I've written this vertex form equation in standard form. The last thing we need to do is put it all together. Can we write an equation for the quadratic function in all 3 forms? Can we first start by writing it in vertex form? So I know from vertex form, what I need to know is my A, H, and K. So luckily on this graph, they kind of tell you what your H and your K are. But we need to look at the pattern of change to really determine what A is. Now luckily that pattern of change is 1, 3, and then 5, okay? So I know my A value is 1. And then they also tell me what my h and k are. So it's going to be minus 4 squared and then minus 4 for k. Okay? Next, we're going to write this same equation in factored form. Now, luckily, we already know what my a value is. So the only thing we need to find are the p and the q. So if I'm looking for the p and the q, really what I'm looking for are those x-intercepts. So on my graph, my x-intercepts are 2 and 6. So this will be minus 2, minus 6. And lastly, we need to FOIL one of these equations or expand one of these equations to write it in standard form. So I'm going to do that over here. So I've got f of x is equal to x minus 2 times x minus 6. So foiling that, I get f of x is equal to x squared minus 6x minus 2x, which combine to give you minus 8x, and then finally positive 12. So now I have written all three forms for a quadratic from a graph.